Our topic is heat exchangers, and in particular we're going to learn how to analyze heat exchangers. There are basically two problems when it comes to heat exchangers. Either select a heat exchanger given that you want the two streams that are trading heat or trading thermal energy, that you want a certain temperature change of those streams, or at least one of the streams. So you have to select a heat exchanger that will do the job. The other possible method, or the other possible problem, uses a different method. Now this particular problem, we can use what's called the log mean temperature difference method. So LMTD can work for basically helping you select a particular heat exchanger that will produce a given exit temperature for the streams. The other problem is to determine the temperature change given a heat exchanger. So if there's already a heat exchanger in existence or in service, what should the exit temperatures be given the incoming, of course, temperatures and the properties of the stream and so forth, and the properties of the heat exchanger. So basically, either selecting a heat exchanger or predicting a heat exchanger's performance. Those are the two problems that we're interested in addressing. Now, turns out the log mean temperature difference method will not work when you're trying to predict how a given heat exchanger will perform. In that case, we have to use something called the effectiveness number of transfer units method. There are a wide variety of heat exchanger types available. There are the big one in the center is an industrial shell and tube heat exchanger. On the right, the little bitty one to the right of that large, sort of looks like a pressure vessel, that's the shell and tube. Well, the one to the right of that is called a brazed plate heat exchanger. Now, I've got some of these that I'll show you in a moment. The one on the left you probably recognize. That's basically the radiator in the front of your car. Without that, your car's engine overheats. So what does that one do? Well, it basically brings in air to cool down hot water. Now, it's got some antifreeze in it, but it's basically hot water. Now, if you think about the purpose of any of these heat exchangers, their goal is always to take an incoming stream and basically slice it up, break it into parts where we can access more surface area of the stream. And so they all do this, but in a different way. The bottom row are a few more heat exchangers. On the bottom left is something much like what you usually call a radiator in your car. But it's actually what I use for heating my home. I heat my home with wood, so I burn wood in a very high efficiency. It's called a boiler, but it doesn't really boil the water, it just makes it hot. But somehow I have to get the heat from that water into my home, right? I have to transfer the thermal energy into the air in the home so I can be comfortable in the wintertime. And the way I do that is with a heat exchanger much like the one in the lower left-hand corner, which is just a cross-flow heat exchanger where the hot water flows through tubes, and there are fins mounted to those tubes, and then you blow air across it. It's the reverse of the radiator. The purpose is not so much cooling the hot water as it is heating the air. The purpose of the radiator is in cooling down the water flowing through your engine to keep your engine cool. Just as in the top center there's a industrial shell and tube heat exchanger, there are smaller versions of these, and if you look down below in the center, that's called a sidearm heat exchanger. It's basically a double pipe heat exchanger where there's a single tube in the middle of it and a shell around the outside. So basically you can flow one fluid through the tube just straight through, and the other fluid flows through the shell around the outside of that same tube, and then of course is contained by an outer tube. Now that's the small brother, if you will, of the shell and tube heat exchanger, because it just has one tube, whereas shell and tube heat exchangers have multiples, and I'll show you a cross section of that in just a minute. The upper right brazed plate heat exchanger I showed you a minute ago, or told you about, is what I use for transferring thermal energy from my boiler to the water inside of the home. Now this is not water that I'd use for bathing in or drinking or anything like this. This is water that's captive inside of my heating system. But it turns out the water that the boiler heats is not the same water that goes through my water to air heat exchanger I already described in the lower left hand corner. And those are two different sets of water, because the boiler sits out in my garage and I've got antifreeze in it. Now the boiler holds about, I think, 50 to 100 gallons of water. I don't remember now, maybe it's 80. And I didn't want to buy antifreeze to fill, too much water. I only wanted to apply antifreeze to the water in the boiler, so I used a plate frame heat exchanger. or a brazed plate heat exchanger, and what that does is that separates the water in the boiler from the water in the home, because the water in the home has the two 500-gallon propane tanks that don't have propane in them, they just have water. That's 1,000 gallons of water. If that water that's inside the home, and by the way, those tanks are buried outside under the ground, so they're not really in my home taking up space in my basement or something, but they sit outside of my the wall. They're buried under dirt and insulated and so forth. But anyway, if I had to treat all 1,000 of those gallons with antifreeze, it would have been extremely expensive, because then I'd be transferring that water to the boiler, and it's got to be treated with antifreeze because the boiler sits outside. It's possible it can freeze, so I need antifreeze in it to keep that from happening. And treating 1,000 gallons of water with antifreeze was just cost prohibitive. It turned out that the brazed plate heat exchanger was cheaper than that much antifreeze. So basically I've got a brazed plate heat exchanger that separates the boiler water from the water that actually goes through the tanks and heats the home. There's a big brother of this that is used in industry called a plate frame heat exchanger. It's on the lower right. And I'll show you more details of all these, but I thought I'd go ahead and show you some of them now. Here's a brazed plate heat exchanger that has been sectioned and cut so you can look at it. Got a mounting plate on the back, and it's been cut into 3 parts. It's been cut this way so we can look at it. We can see multiple stacks or multiple plates here, and on the inside we see a lot of blockage, right, or pieces of metal that are supposed to make the flow turbulent and separate the flow out. Now if we take the other half, we've also cut it so you can see inside and see all of the features that are there to break up the fluid, whatever fluid's flowing through this, break it up more, and thereby expose the fluid to more surface area. So you probably have some cross-flow heat exchangers besides the one in your car, in the front of your car, that's your radiator for your vehicle. You probably have an air conditioning system in your home. If you have central air conditioning, then you've got ductwork that pulls air through the ductwork, and it has to be cooled. How is it cooled? Well, there are a couple of heat exchangers that cold refrigerant flow through the pipes, and air runs across. And it's much like the cross-flow heat exchanger I described that keeps my house warm, except it's usually called an A coil. And the reason it's called an A coil, you can see, is because it's really 2 flat heat exchanger that are set up in the shape of an A. And the reason for this is because it all has to fit inside of ductwork, where you're pulling air through it, and you want more surface area, you want more flow area. And so the flow, you can see the insides of what's called an air handler on the right with a blower up at the top. You can't see the blower, unfortunately, but you can kind of tell it's got an axis of rotation that's horizontal in this view. And you can see the A-frame heat exchanger. Air enters the bottom. You can't see it in the pictures I've selected, but the bottom is open. If you look at the left picture, the bottom is open and air can easily get in there. And then the air has to kind of turn to go through the 2 sides and then recombine going through the fan. So that's called an A coil, and it obviously it always has refrigerant flowing through it, whether it's a heat pump or an AC system. But by setting it up in this shape, you don't have to have as much cross-sectional area of flow or cross-sectional area in your ductwork, and yet you get a larger cross-sectional area of flow through the heat exchangers. So that's an interesting configuration that saves some space. The shell and tube heat exchangers, I've got an example of one. It's been sectioned, and so this is a small one, but these come in sizes that are much, much larger than I could even hope to lift. There are shell and tube heat exchangers that weigh much more than your vehicle, for example. They could easily weigh 10 tons. And these are interesting because they're a heat exchanger, but they're really not the most compact type of heat exchanger. Let me open it up so you can see. On the inside of this, you can see how the tubes have all been sectioned. And you can see that there are these lines. At least I hope you can see that in the video. There's all these lines. And the lines actually are baffle plates. Now if you look at the picture, you can see the purpose of baffle plates. See, here's how it works. Fluid flows on the shell side here around the outside of the tubes. Okay, so it's on the outside of the tubes. It's on what's called the shell side. But other fluid flows through the tubes themselves. Okay, so there's actually, if you look at this carefully, you'll notice that there's 4 banks of tubes. I'll explain why that is here in just a second. But the purpose of the baffles is so that the shell fluid doesn't just flow right across the tubes and not really interact very much. The baffles force the shell flow to go around and cross over the tubes, and this enhances the heat transfer. Now, why would you use a shell and tube heat exchanger? Why would that be a choice, or why would that be an optimum choice? Well, one reason is if you have a fluid that's flowing, one of the two fluids, and let's say it has some mud in it, or maybe it has, maybe it's hard water, and so there could be calcium deposits that come out of the water and deposit on some surface. Well, you need some way of cleaning the heat exchanger. Many of these heat exchangers, like this one that I sectioned before, this brazed plate, can't be cleaned, at least not mechanically. It can only be cleaned chemically. And so if you have a fluid flowing that is liable to leave some junk behind that needs to be cleaned, it's handy to have tubes, because you can often take the end off, see, and have access to the tubes and clean it. In fact, this is very common in industry, to take the heads off the end of the shell and tube heat exchangers, and now you've got access to the tubes and you can clean them all out. Now, there are variations on this. There are shell and tube heat exchangers where the tubes make a U shape. Okay, so you can see I've got an image of that. But the most common configuration has a cap essentially on either end, so that you can access the tubes and clean them out. So you would always choose, or at least it would be wise, to choose to have the more dirty fluid, the fluid that's going to lose something, leave something behind, go through the tubes rather than the shell, because the shell is hard to access and clean out. And as you can imagine, the shell has to be sealed and the tubes have to be sealed. My father has been a welder as long as I can remember. He's worked on all kinds of things. One of the things he worked on were oil rigs, so he's lived out on oil rigs and been a welder there. And he was talking about the talent that some welders have. You can see the picture here. You can see that there can be thousands of tubes in some of these shell and tube heat exchangers. And he was talking about some heat exchangers like this where he saw a welder that had to fix it. Well, the problem is one of the tubes was leaking, and there's basically an end plate. I'll try to kind of show you this on video. Hopefully it's not out of focus, but there's an end plate here, and you got to seal the end of the tube to that plate. Well, this is just a copper and brass heat exchanger, so this one's pretty easy. You just braze it, right? But a lot of these shell and tube heat exchangers are made of steel, and so he was talking about how he's seen welders that work on these types of heat exchangers where they have to repair it. Well, you can't just take all the tubes out, right? That's not the way to do it. He said he's seen welders take a welding rod, bend it around 180 degrees, put a mirror back there because they can't access it, and weld backwards and yet make a perfect weld bead. That's pretty impressive welding. I imagine those guys and girls make a lot more than any of us will ever make, because that's some pretty serious talent. But anyway, so shell and tube heat exchangers can be a real pain to build and to seal, but they're also very useful when you have a fluid that you'll need to clean out. Now, I mentioned that the ends of these have 4 regions. If you notice, it's broken up, let's see, into sort of a cross pattern, a sort of a horizontal and vertical line. And you'll notice that the end that I've got here has 3 different regions. Now, this one's failed. There's some chunks out of the material here. But you notice there's a region here, there's one here and here, and basically this is an inlet, and what happens is the fluid comes into 1/4 of the tubes. So if we look at the tubes, it'd come into just 1 quadrant, right? So 1 quadrant of the tubes would have flow going through, and then the other end, I don't have the other end, but the other end would look a lot like this. It would just have 2 of these larger areas without that blockage. And so what would happen is, once the fluid goes in 1/4 of this, it would come to the other end, go into another quarter, come out, be redirected back into another quarter by this end, reflected back, and come out here to the exiting port, the opposite port it entered on, or entered from, to leave the heat exchanger. So whereas in the cross-sectional picture I've got there, you see that the inlet and exit on the shell side are on the opposite end of the heat exchangers. This one has the shell side entering and exiting on the same side of the heat exchanger. So it's sort of like a cross between the cross-section version you see in the YouTube. So it's possible to have a multi-shell and or multi-tube pass heat exchanger when you're talking about a shell and tube heat exchanger. If you look at the image with the U-tubes in the sort of the center of my slide, that would be a 2-tube pass heat exchanger. Double pipe heat exchangers are kind of like the shell and tube heat exchangers. They're just smaller. There's a single tube, and you can see a cross section of 2 of them down at the bottom of my slide. And we need to start looking at these and thinking about them, because there's a fundamental question here. Do we want the 2 fluids to flow in the same direction or opposite directions? You might think the same. That way, you know, both the hot and the cold fluid come in on the same end of the heat exchanger, and you got the highest temperature hot fluid with the coldest temperature cold fluid. Heat exchange should be fast, and that's really our goal, right? We want, I mean, the reason you put a heat exchanger into service is to exchange heat between 2 fluids, not to resist heat, right? So we like for it to go as fast as possible. So you might be tempted to run heat exchangers in what's called parallel flow. But think about the maximum and minimum temperatures that the exiting streams can take on. The hot fluid will be decreasing its temperature as the fluid moves along the length of the heat exchanger, and the cold fluid will be increasing its temperature. And so they'll be getting closer and closer together, and eventually will come out as sort of an average of the 2 temperatures, right? If you instead run the heat exchanger in what's called countercurrent flow, where one fluid goes one way and the other fluid goes the other way, well, then the hottest hot fluid is in contact with the hottest part of the cold fluid. Now, if you need to pause for a minute and think about that, make sure you do. Think of the hot fluid in the counterflow configuration as being on the shell side, and the cold fluid being on the tube side. Okay? So on the left-hand side of our counterflow heat exchanger, you've got the cold fluid exiting the pipe at pretty much its highest temperature, and yet it's still in contact with the hottest portion of the hot fluid, so there's still a temperature difference, so we can still transfer some heat into the cold fluid. So really, counterflow allows us to use a heat exchanger most effectively. Okay? And there's a term called effectiveness of heat exchangers, and it's something that we really care a lot about. It's how effective is the heat exchanger? At least in English, that's the way we'll define it, but we'll define it mathematically as well. So counterflow is actually usually a desirable configuration. Now, in my wood system, my wood heating system, the exhaust gases actually come into a heat exchanger that's a lot like this, just turned on its side. And so the exhaust gases come into some tubes, which makes sense because you need the ability to clean the tubes. It's the exhaust gases that are most likely to be dirty, right? So they come in, and the way the boiler is designed is for the water to also flow upward instead of downward. And if you think about that, that means that my boiler's heat exchanger is parallel flow, which is not the most effective configuration. I've often wanted to change the pump direction just to find out if I could make it work. There's a reason, though, that it's set up in parallel flow. If you lose power to, electrical power, well, then the boiler has lost control, the fan can't blow air in, the temperature can't be regulated automatically, and the pumps don't work anymore to pump water from the boiler out to the rest of the system and remove thermal energy from the boiler. But the fire is going to keep burning, at least for a little while, right? And so that fire is going to keep giving off energy. That energy has to go somewhere. If you don't have a place for that energy to go, well, then the boiler is going to overheat, the pressure valve opens, and now you've thrown a bunch of antifreeze away and you've got a mess to clean up. So why then do they make it run parallel? Well, the reason is because you're supposed to have what's called a dump zone. Basically, the idea is that warm water would be buoyant. And so if there's no pump to make the water flow, the warmth of the water will make it buoyant, and it will flow automatically anyway and can go through a heat exchanger in your home, giving your home some heat, but basically removing heat from the boiler so the boiler doesn't overheat. So that's the whole reason for setting up the heat exchanger to flow in the same direction. It's a valid reason. Now, in my case, I don't have a dump zone, so there's really no advantage to this configuration. And so what I'd like to do is run it in the opposite direction, make the water flow down as the exhaust gases flow up, and see if I could extract just a little more energy from the exhaust gases before they leave the stack. That would translate into a little bit less wood that I have to load in the boiler, and a little bit higher efficiency. I showed you the sectioned brazed plate heat exchanger, and I mentioned that you can't take these apart and clean them mechanically. You have to clean them chemically, if anything. In industry, that's not acceptable because a lot of times you need the ability to flow a fluid that's going to leave some deposits behind, and therefore you must be able to clean the heat exchanger out by taking it apart and cleaning it mechanically. So a plate frame heat exchanger is kind of the big brother to this small brazed plate heat exchanger, and it's simply a bunch of plates that are mounted together and squished together, and you've got these tension rods you can use to just tighten the two fixed covers onto either end. And the advantage here is you can take it apart and clean it, but also you could take it apart and add more plates if you wanted to, and in effect have a larger or more effective heat exchanger because there's more area for heat transfer. Now you need to wrap your head around the way this works, and I've got an animation that might help you in just a second, but the idea is that the ports are carefully gasketed, so all of the cold fluid flows through every other plate, and it's not allowed to mix with the hot fluid. So you see the blue arrows going up, and hopefully you notice those are two plates that are sandwiched between a hot plate. Okay, and so the hot fluid goes in on the upper right hand side. It flows down between each alternate plate. The cold fluid comes in on the lower left hand side and flows up through each alternate plate that is not a hot plate, and then recombines and comes back out the top. Now the reason that this works, the reason you're able to make this flow work and the flow does distribute amongst all the plates, is because that pipe, and it's not really a pipe, right, but it's effectively a long cylinder that's made up. That long cylinder has low resistance to flow, but the plates are so close together and often have waviness or some other feature built into the plate to enhance heat transfer by increasing surface area. So often there's that resistance to flow that the fluid will naturally separate out into all of the plates fairly well. So this is a plate frame heat exchanger, and it's got the advantages of a shell and tube heat exchanger, but it's a much more compact heat exchanger, so it has a lot of surface area in a very small area. In fact, there's something called the beta, the compactness of a heat exchanger, and you can calculate it pretty easily. You can define it as the area available for heat transfer divided by the volume that the whole unit takes up. So if you look at a shell and tube heat exchanger, they are not very compact heat exchangers, but you can clean them out. They're relatively simple to build. A plate frame heat exchanger, on the other hand, is a fairly compact heat exchanger because in that volume that the heat exchanger takes up, there's a whole lot of area packed in there. So anything arbitrarily that it's set that anything that's got a ratio of about 700 square meters per cubic meter, or in English units 200 square feet per cubic foot, is classified as a compact heat exchanger. Here's an animation of the plate frame heat exchanger in operation. You can see the fluid flow. So you see the hot stream coming in the lower left, separating into the various plates, and then recombining. Now, not all of the heat exchanger is shown. There would be more going to the left, okay, but there's eventually some plate that blocks all the flow, and it all has to come back out the front. And you see the cold stream on the upper right side coming in and going into the other alternate plates, and then recombining and coming out lower right. Now, as I said, this is a compact heat exchanger. You actually have something that's much like a compact heat exchanger in your body. If you look at your lungs, there are bronchial tubes that spread out, and it turns out that you have a heck of a lot of surface area inside of your lungs. I don't remember how much it is, but I think it's on the order of a football field or so of area. You can look it up and find out. It's a whole lot of area. It's kind of interesting the way that the bronchial tubes branch out, because they have an optimized fractal type pattern that concentrates a lot of area into a very small volume. And this is the reason why in the wintertime you can breathe in cold air, right? You breathe it in, let's say it's 0 degrees Celsius outside, you breathe it in. As soon as you bring out that air, yeah, you're breathing out some waste products, but you're basically breathing out the same thing you breathed in. Most of it's nitrogen anyway. So you breathe in cold nitrogen and you breathe it out hot nitrogen. Thank God there's some oxygen in it, or we'd all be dead. Either that or we'd work somehow differently. I don't know. But anyway, so you breathe out this air, and what was cold just a few seconds ago is now really warm air. How did that happen? Well, your bronchial tubes basically took in that breath of air and cut it into really small pieces. and then when it comes back out, it's basically picked up thermal energy from the bronchial tubes and whatever's in your lungs that has, thermal energy and is at your body's temperature. So you're carrying around something that's a whole lot like, well, two of something that's a whole lot like a compact heat exchanger. Cross-flow heat exchangers are a lot like the radiator in your car. There's really two different kinds that are fairly common. There's the type that have fins and the type that don't. Basically, there's the type, as you see on the left, where you've got tubes and one fluid flowing through it, and then fins that separate the air or gas, typically, flowing across those tubes, thus the name cross-flow. But this is a so-called unmixed cross-flow heat exchanger. And the reason it's called unmixed is because as soon as the air or gas or whatever it is that goes in between the fins, as soon as it's between the fins, it has no option to go to some other fin, right? It has to go through that same fin. So that air is unmixed. Whereas if there are no fins, if it's just flowing across some tubes, well then, it can mix all it likes, right? So on the tube side, whatever fluid flows on that side is always unmixed, in the sense that fluid's not going to just jump from one tube to another as it flows along the length of the tube. That's not possible. You'd have a leak in the tube, well, a leak in two tubes if that happened. Now there's another interesting idea for a cross-flow heat exchanger that's a little bit different than this, and there's a crude model of it shown there at the bottom of the screen, but I included it because I found it interesting. A different type of cross-flow heat exchanger. Now the type you see at the top would typically be used for a gas that is transferring thermal energy with a liquid. And if you remember anything about the convective heat transfer coefficient in gases, they're usually a lot lower than the heat transfer coefficients in the liquid. And so it's helpful to have fins on the air or the gas side. If you think about your radiator, you may wonder, are there fins on the inside of the tubes also? Well, the answer is no. And the reason there are no tubes is, number one, it'd be difficult to manufacture, but number two, the fact is you don't need them. The heat transfer coefficient in the liquid, the antifreeze and the water in your car, is high enough that it wouldn't be effective, it wouldn't be very useful. So we've got this idea of an unmixed or a mixed flow, and typically we're talking about in the gas that's flowing, the gas fluid.